Welcome back to the Deep Dive, everybody. Today we're going deep on an element. And I bet most people, they don't think about it every day, but it's actually in a bunch of stuff around us.
Yeah, it really is more prevalent than I think a lot of people would think.
Yeah.
It's boron.
Boron.
And it's a really interesting element that has a lot of really cool applications and some really interesting chemistry.
Yeah, and I think, even before we get into the nitty-gritty of boron,
Right.
it's even got an interesting, discovery story.
Yes, absolutely. It wasn't recognized as an element until 1808.
Really?
So relatively recent. And there were multiple people that were all working on it around the same time.
Wow.
Humphrey Davy, a famous chemist,
Wow.
he was the first one to start working with it, and he was doing electrolysis of borates, using
Wow.
electricity to break apart compounds. And he started to see hints of this new element, and later on, he actually was able to use potassium to reduce boric acid, and he called it borosium. That was his name for it at the time.
Borosium.
Yeah.
I kind of like that.
Yeah, it's got a ring to it.
Yeah.
But at the same time, over in France, Gay-Lussac and Thénard, they were also working on isolating this element, and they were using high temperature and iron to reduce boric acid. They also figured out that boric acid is the oxidation product of boron when it reacts with air.
Oh,
So
interesting.
you've got these multiple people all working on it at the same time. It wasn't really until 1824 that Berzelius actually identified it as the element boron that we know today. And then the first pure sample of boron, at least relatively pure, it wasn't made until 1909 by Ezekiel Weintraub.
So it took quite a while to really pin it down.
It did, yes.
Well, let's get down to, the actual element.
Okay.
What makes boron, what is it? Let's start there.
Boron is, well, as you said, an element, and it's got some really interesting properties. One of the things that I find particularly interesting about it is that it has an isotope, boron-17, that exhibits what's called a nuclear halo.
Okay, I saw that in my research, but nuclear halo, I don't think I fully grasped that one.
So it's a really strange phenomenon, and it happens with certain isotopes of certain elements where you have a core, and then some of the neutrons kind of orbit further out than you would normally expect, almost like a halo around a planet.
Huh, okay.
So they're very weakly bound to the nucleus, and it kind of gives them this sort of diffuse structure.
That's weird. Atoms are strange.
They are very strange.
Okay, so I also know that boron has two stable isotopes.
Yes.
Boron-10 and boron-11. And these are really important for NMR spectroscopy.
Yes, they are. Both boron-10 and boron-11 have what's called a nuclear spin. Boron-10 has a spin of 3, and boron-11 has a spin of 3/2. And because of this spin, these nuclei can interact with a magnetic field, which is the basis of NMR. You can actually get commercially available spectrometers specifically for detecting boron-11.
Really?
Yeah, and so that's a really powerful tool for chemists, particularly for organic chemists.
And I know that NMR is all about figuring out, structures and, how molecules are put together.
Right, exactly. So one of the things that boron-10 and boron-11 do that's really useful is that they can cause splitting in the NMR signals of any atom that's directly bonded to them. And this is really helpful for figuring out how things are connected.
So boron's, helping us map out the, molecular world in a way?
It is.
Yeah, cool. Now, let's talk about some of the, compounds of boron. We've talked about the element itself, but boron, loves to make friends.
Yes, it does.
What are some of the, trends or common things that we see with how boron bonds to other elements?
Well, one of the things that we see with borate anions, which are negatively charged boron atoms bonded to oxygen,
Okay.
is that they tend to condense and form larger structures.
What do you mean condense?
So they form oxygen-boron bonds, or BOB bonds,
Okay.
and these bonds are really strong, and they allow borates to link up into these bigger, more complicated networks.
So they like to, build chains and,
Exactly.
complex structures.
And this BOB linkage isn't limited to just borates. We also see it with borosilicates, which are bor-on-oxygen silicon bonds, and borophosphates, which are bor-on-oxygen phosphorus bonds. And these are really important, and they occur in nature in a lot of minerals, and they're also synthesized for various applications.
Okay, so we see these kind of building block units being able to link up to make bigger structures. What about something like alkoxides or boronic acids? What are those all about?
So alkoxides are basically boron bonded to 3 OR groups.
Okay.
So the R is just representing an organic group, and so you have boron with 3 oxygens, and each oxygen has an organic group attached to it. Boronic acids, on the other hand, they have 2 organic groups that are directly bonded to the boron, and then the boron also has an OH group on it.
Okay.
And there are lots and lots of different variations of these types of compounds, and they're used in all sorts of things. But one of the areas where they're really important is in pharmaceutical synthesis. So a lot of drugs are made using organoboron compounds, and one of the key reactions that's used to make these compounds is the Suzuki reaction.
Ah, the Suzuki reaction. I've heard that name before.
Yes, and this is a really powerful reaction. It allows you to form carbon bonds, which is like the backbone of organic molecules. And it was such an important discovery that Akira Suzuki won the Nobel Prize in Chemistry in 2010 for his work on this reaction.
Wow.
So that really highlights how important boron is in the pharmaceutical industry.
Yeah, you don't often think about like boron being a part of making medicines, but it's amazing.
It is, yes.
So speaking of organoboron compounds, we've touched on them a little bit, but let's dig deeper into those. What really defines an organoboron compound?
So organoboron compounds are compounds that have a boron-carbon bond.
Simple enough?
Yeah, and the primary way to make these compounds is through a reaction called hydroboration.
Okay, hydroboration. I need you to break that down for me.
So hydroboration is basically the addition of a boron-hydrogen bond across a double bond or a triple bond in an organic molecule.
Okay.
So you have carbon double bond, and then you add boron and hydrogen across that double bond, and now you have a boron atom attached to one of the carbons.
Okay.
The classic reagent for this is diborane B2H6, and one of the kind of classic examples is the preparation of triactylborane, which is made by reacting diborane with hexene. And in this reaction, the boron ends up adding to the terminal carbon, the end of the carbon chain.
So it has like a specific place where it likes to attach.
Yeah, and that's called regiochemistry.
Okay.
And it's because the boron-hydrogen bond is polarized. So boron is slightly positive and hydrogen is slightly negative.
Okay.
And so the boron tends to go to the less sterically hindered carbon, which is usually the terminal carbon.
So it's like predictable, like chemists can rely on this.
Exactly, and that's why it's such a powerful reaction. And H.C. Brown actually won the Nobel Prize in Chemistry in 1979 for his work on hydroboration.
Wow, another Nobel Prize.
It's a really, really important reaction in organic synthesis.
Boron's got quite the track record.
It does, yes.
Now, in my research, I also saw something about these boranes being a little bit, shall we say, reactive?
Yes, they are. A lot of the boranes, especially the smaller ones and the alkyl boranes, they're very volatile and they can ignite spontaneously in air.
Oh.
So they're very pyrophoric. And so you have to be very careful when you're working with them. In fact, there was some work done in the 1950s on using boranes as fuel additives for jet fuel. They called it zip fuel.
Wow.
But there were safety concerns.
Understandably.
Yeah.
Now, in terms of the structure of these triorganoboron compounds,
Okay.
what do they look like generally?
So generally speaking, when you have a triorganoboron compound, meaning you have 3 organic groups attached to a boron,
Okay.
they tend to be trigonal planar. So the boron is in the middle, and then you have the 3 organic groups arranged around it like a triangle, all in the same plane.
Okay.
Flat, yes. And they also tend to be weak Lewis acids.
Okay.
So that means they can accept a pair of electrons from a Lewis base. So a Lewis base is something that has a pair of electrons that it can donate.
Okay.
And when a Lewis base donates its electrons to the boron, it forms what's called an adduct, and the geometry around the boron changes to tetrahedral.
So it goes from flat to like a pyramid shape.
Exactly,
Yeah.
And this is different from the triorganoaluminum compounds, which are kind of similar in some ways, but they tend to form more complex structures with bridging alkyl groups.
So just, slight differences in how those electrons are arranged leads to big changes in how those compounds behave.
Exactly, yes.
Fascinating. I also, in my notes, I came across something about a really recent discovery about a boron-carbon triple bond.
Yes, this is very new. Just this year, actually, 2025, a group of chemists was able to synthesize a compound that contained a boron-carbon triple
A
bond.
triple bond.
Yeah, and this is really significant because for a long time, it was thought that boron-carbon triple bonds were too unstable to exist.
Interesting.
But they were able to synthesize it, and they were able to characterize it, and it's a stable compound. And this is potentially really groundbreaking because it opens up a whole new area of chemistry.
Yeah, we've got single bonds, we've got double bonds, and now we've got triple bonds
Exactly.
with boron. So who knows what's next?
Who knows? Yeah.
All right, let's switch gears a little bit. Let's talk about boron nitrides. How do boron and nitrogen like to bond to each other?
So boron nitrides are really interesting because you predominantly see just boron-nitrogen bonds. You don't really see boron-boron bonds or nitrogen bonds. And the reason for this is that boron and nitrogen together have 8 valence electrons, which is the same as 2 carbon atoms.
Okay.
And so this leads to some really interesting structural similarities between boron nitrides and carbon allotropes.
Allotropes meaning like the different forms that carbon can take.
Exactly. So for example, you have cubic boron nitride, which is often called borazon. And this has a tetrahedral structure, just like diamond.
Oh, wow.
And it's extremely hard. It's actually one of the hardest materials known.
So it's right up there with diamond in terms of hardness.
It is, yes.
Amazing.
And then you have hexagonal boron nitride, which is analogous to graphite.
Okay.
And it consists of sheets of boron and nitrogen atoms that are arranged in a hexagonal pattern. And these sheets stack on top of each other. And like graphite, it's a good lubricant.
Okay.
But unlike graphite, it's not a good conductor of electricity.
So subtle differences, but big changes in the property.
Exactly, yes.
Interesting. I also saw something about borazine. Where does borazine fit into all this?
So borazine is a molecular analog of benzene, and it has a 6-membered ring structure with alternating boron and nitrogen atoms.
Okay.
And it's sometimes called inorganic benzene
Okay.
because it has this ring structure that's similar to benzene, but it's obviously not an organic molecule.
Got it. Okay, well, let's move on to borides. What are borides?
So borides are compounds that are formed between boron and a metal.
Okay.
And they tend to be very hard, and they have very high melting points. So, for example, titanium diboride, zirconium diboride, and hafnium diboride, they all have melting points above 3,000 degrees Celsius.
3,000 degrees. That is crazy.
It's very high.
So what are those kinds of materials used for?
They're often used as hard materials, like in cutting tools and things like that.
Makes sense. They got to be really tough to withstand those kinds of temperatures.
Exactly, yes.
Now, I also saw magnesium diboride mentioned in my notes. What's special about that one?
So magnesium diboride is a superconductor,
Okay.
and it has a relatively high transition temperature of 39 Kelvin.
Okay.
And so it's actually used in a lot of different applications. For example, CERN, the European Organization for Nuclear Research, they're using magnesium diboride cables for high current applications.
So boron's like powering the Large Hadron Collider.
So it's playing a role, yes.
That's so cool.
Yeah.
All right, let's take a step back and think about boron, in the grand scheme of things. Where does it actually occur in nature?
So boron's origin is kind of interesting. Unlike a lot of the lighter elements, it's not really formed in stars. It's actually formed through what are called spallation reactions.
Okay, spallation. Another new word.
Yeah. So spallation reactions happen when you have high-energy cosmic rays that collide with heavier atomic nuclei, and they basically smash them apart.
Okay.
And these fragments, they include things like boron. So boron is actually a product of these cosmic collisions.
Wow, that is so cool. So it's like literally coming from outer space.
It is, yes.
Wow. Okay, so here on Earth, where do we find boron?
So boron doesn't occur as a free element on Earth. It's too reactive.
Okay.
It reacts very readily with oxygen, so we find it in various borate minerals.
Okay.
So things like borax, kernite, ulexite, culminite. These are all borate minerals that are typically found in arid regions like dry lake beds, where they formed from the evaporation of water that was rich in boron.
So geographically, we're talking about like deserts and places that used to be, bodies of water.
Exactly, yes.
Interesting. And I know that some places are richer in these boron deposits than others.
Yeah, Turkey actually has about 73% of the world's borate reserves.
Wow, 73%.
Yeah, it's a lot. And then the United States, particularly California, also has significant deposits.
Okay. So speaking of resources, where it comes from, how much is there? I know that global demand for boron has been increasing. What's driving that increase?
So there are a couple of factors that are driving the increase in demand for boron. One of them is the growth in the production of glass fiber and fiberglass.
Okay.
So boron is often added to glass to improve its strength and durability. And fiberglass is used in all sorts of things, from construction to automotive to aerospace.
Yeah, it's everywhere.
It is, yeah. And then the other factor is the increased use of borosilicate glass,
Okay.
which is the type of glass that's used in Pyrex and other heat-resistant glassware.
Right, yeah.
And borosilicate glass is also used in a lot of other applications, like solar panels and LCD displays. And so with the growth of these industries, the demand for boron is just continuing to increase.
So boron's kind of like a hidden ingredient in a lot of the stuff that we rely on in our everyday lives.
It is, yes.
Okay. Well, let's get into some of those applications then. Let's start with boronated fiberglass. What's the role of boron in fiberglass?
So, as I mentioned earlier, boron is often added to glass to improve its strength and durability.
Okay.
And when you add boron to fiberglass, it does the same thing. It makes the fiberglass stronger, more durable, and more resistant to heat and chemicals.
Okay.
And there are different types of boron-containing fiberglass that are made for different applications. So, for example, E-glass, which is short for electrical glass, is an aluminoborosilicate glass that's often used for electrical insulation. And C-glass, which has a higher boron oxide content, is often used for things like staple fibers and insulation. And then D-glass is another type of borosilicate glass that's used in applications where you need a low dielectric constant, like in some electronic applications.
Okay, so it's kind of like a tuning knob
Yeah,
that you can use to adjust the properties of the fiberglass depending on what you want to use it for.
exactly.
I know that boron-containing fiberglass is pretty much the biggest use of boron globally.
It is, yeah. Over half of the boron that's produced globally goes into making boron-containing fiberglass.
Wow, that's a lot.
It is, yes.
Okay. Let's talk about borosilicate glass, the stuff that Pyrex is made of.
Okay.
What makes borosilicate glass so special?
So borosilicate glass is different from regular glass because it has a very low coefficient of thermal expansion.
Okay, and what does that mean?
It means that it doesn't expand or contract very much when it's heated or cooled.
Oh.
And so it can withstand sudden changes in temperature without breaking.
So that's why you can take a Pyrex dish out of the oven and put it right into cold water, and it won't shatter.
Exactly, yes.
That's pretty handy.
It is, yeah. And borosilicate glass is also very resistant to chemicals.
Okay.
So it's often used in laboratory glassware and other applications where you need a material that can withstand harsh conditions.
So we've talked about boron being used in these, compounds like fiberglass and borosilicate glass. But what about elemental boron? Does it have any applications on its own?
Yes, it does. Elemental boron can be made into fibers,
Oh,
and these fibers are very strong and lightweight.
okay.
So they're often used in high-performance composites, like in aerospace applications.
It's like airplanes and spacecraft and things like that.
Exactly, yeah. In fact, boron fibers were used in the early stages of the development of the SR-71 Blackbird.
Wow, the Blackbird.
Yeah, which is a very high-speed reconnaissance aircraft.
That's so cool. So boron's like part of spy plane technology.
It is, yes. That's awesome. But boron fibers are also used in other applications, like in microelectromechanical systems or MEMS.
Okay, so really high-tech stuff.
Yes, they are.
Okay. I also know that boron is used in a lot of hard and abrasive materials.
It is, yes. Boron carbide is one of the hardest materials known. It's the third hardest material, after diamond and cubic boron nitride.
Wow, third hardest. That's impressive.
It is, yeah. And so boron carbide is often used as an abrasive in grinding and polishing applications. And cubic boron nitride, which we talked about earlier, is also very hard, and it's often used in cutting tools.
So boron is really important for making the tools that we use to make other things.
It is.
Okay. We've also mentioned borates a couple of times. What are some of the uses of borates, like borax?
So borax is used in a lot of different things. It's used in laundry detergents, soaps, and other cleaning products.
Okay.
It's also used as a flame retardant.
Okay.
And it's used in the manufacture of fiberglass and borosilicate glass, which we've already talked about.
All right, so it's kind of like a jack of all trades.
It is, yes.
Okay. Let's talk about the semiconductor industry. How is boron used in semiconductors?
So boron is used as a dopant in silicon semiconductors.
Okay.
And what that means is that it's added to the silicon in very small amounts to change its electrical conductivity.
Okay.
And specifically, boron is used to create what's called P-type silicon, which is silicon that has a deficiency of electrons.
Oh.
And P-type silicon is essential for making transistors and other semiconductor devices.
So it's basically controlling how electricity flows through those materials.
Exactly, yes.
Wow. Okay. And I know that boron is also a key component in magnets.
It is, yes. Boron is used to make neodymium magnets,
Okay.
which are the strongest type of permanent magnet.
Wow.
And neodymium magnets are used in all sorts of things, from hard drives to electric motors to wind turbines.
So again, we see boron in these really high-tech applications.
Exactly, yes.
Okay. I also came across some information about boron being used in nuclear applications. What's that all about?
So boron 10, which is one of the isotopes of boron,
Right.
is very good at absorbing neutrons.
Okay.
And so it's used in control rods in nuclear reactors to control the rate of nuclear fission.
Okay, so it's like a safety feature.
It is, yes.
Makes sense.
And boron is also being investigated for use in fusion reactors
Okay.
because it can help to reduce the amount of neutron radiation that's produced.
Okay, so boron is like helping to make nuclear power safer.
Yes, it is.
That's great. I also came across something called neutron capture therapy.
Okay.
What is neutron capture therapy?
So neutron capture therapy, or BNCT, is a type of cancer treatment.
Okay.
And it works by using a non-radioactive isotope of boron, boron 10, to target tumor cells.
Okay.
And the boron 10 is delivered to the tumor cells, and then the tumor is irradiated with neutrons. And when the boron 10 absorbs a neutron, it undergoes a nuclear reaction that releases high-energy particles that kill the tumor cells.
Wow.
And BNCT is being investigated as a treatment for a variety of different types of cancer, including brain tumors, head and neck cancers, and melanoma.
So it's like a really targeted way of treating cancer.
It is, yes. It's very precise.
That's really cool. I also saw a couple of other, I guess, smaller applications of boron, like in welding and metallurgy.
Yeah, so borax is often used as a flux in welding and soldering.
Okay.
And a flux is basically a substance that helps to prevent oxidation of the metal surfaces that are being joined.
Okay.
And boron is also used as an alloying element in some metals to improve their hardness and strength.
Okay, so it's kind of like a behind-the-scenes helper in a lot of these processes.
Exactly.
Yeah, okay. What about in adhesives and polymers?
So borax is sometimes used in adhesives to improve their bonding strength.
Okay.
And it can also be used as a cross-linking agent in some polymers. And cross-linking is basically a process of forming chemical bonds between polymer chains.
Okay.
And this can improve the properties of the polymer, like its strength and its resistance to heat and chemicals.
So again, we see boron being used to like tweak and improve the properties of materials.
Exactly.
Yeah, yeah. I also came across a really interesting historical use of boron. It was used in rocket propellants.
Yes, it was. Triethylaluminum triethylborane, or TATEB, was used as an igniter for rocket engines.
Wow.
And it was used in the Saturn V rocket, which was the rocket that launched the Apollo missions to the moon.
That's amazing. So boron helped to get us to the moon.
It did, yes.
Wow. Okay, let's talk about the biological role of boron. I know it's essential for plants, but what about animals and humans?
So boron is definitely essential for plants. It involved in a variety of processes, including cell wall formation, sugar transport, and hormone production.
Okay.
But its role in animals and humans is less clear. There's some evidence to suggest that it might be involved in bone health, brain function, and immune function. But more research is needed to really understand its role in animal and human health.
Okay, so it's still kind of a mystery.
It is, yes.
But I did come across a really interesting hypothesis about boron and the origins of life.
Oh, yeah.
The idea is that boron might have played a role in the formation of RNA on early Earth.
Yes, that's right. The hypothesis is that boron could have helped to stabilize RNA molecules, which would have been essential for the development of life as we know it.
Yeah.
And there's even some evidence to suggest that boron might have been more abundant on early Earth than it is today.
Wow, so boron might have been like a key ingredient in the primordial soup.
It's possible, yes.
That's fascinating. Well, we've covered a lot of ground today. We've gone from the discovery of boron to its role in the origins of life. And I think it's safe to say that boron is a truly remarkable element.
It is, yes. It's very versatile.
Yeah. And given its unique chemistry and its wide range of applications, I think it's exciting to think about what the future holds for boron.
Absolutely.
Who knows what amazing new discoveries and innovations are waiting to be made.
Who knows? Yeah.
Well, I want to thank you for joining me today on this deep dive into the world of boron.
It's my pleasure.
And thank you all for listening to The Deep Dive. We'll see you next time.
Thanks for having me.
Of course.